Thank you so much for all of your questions as well. If you have questions this week, I am going to stretch my limits as what I think I can do as a teacher. This is going to be a pretty dense week. We are going to be talking about some of the most complicated theoretical physics, up to and including something called inflationary theory, along with quantum theory. We're going to be talking about a lot of weird stuff, and I'm going to try to make this accessible to the layman, so that you can sort of understand what's going on. So if you do have questions this week, if I've done a bad job trying to make this accessible, please ask. Do not feel bad. This is complicated stuff. It's taken me years of study to even get my head around a lot of it. So if this is somehow I can't cram years of study into an hour, please don't feel bad if you have questions, or if you want to stick around after class and talk with me a little bit further. So I want to talk about something called the fine-tuning of the universe. That's what we're discussing today. And this is essentially how the fine-tuning argument goes. When we look around the universe, we see that there's different properties the universe has. For example, the strength of gravity, or how strongly atoms bind together, things like that. How fast the speed of light is even. There's these physical attributes that seem to be innate qualities of the universe itself. They're not really changing or anything else. There's these properties. And we discovered something really interesting about these properties. They're extremely finely balanced. And we're going to discuss exactly how finely balanced today, but it would not be an exaggeration to describe this as balancing a coin on the edge of a razor blade. They're incredibly finely balanced. In fact, that would probably not nearly be enough. And what we see is if any of those attributes, the innate properties of the universe, were just a little bit different, not only do we not exist as humans, because the universe would be incompatible for life, but in many cases, stars can't form, galaxies can't be there. Like the universe itself can't actually be here. So that's essentially what we're talking about. And the question is why? Why is this? And physicists have been noticing this for almost 50 years now, and they've been trying to figure out, okay, why is it just so precise? Like, why can't we have the gravity be just a little bit different? And there isn't a good explanation for it in the naturalistic world. It seems that it's so bad, it just doesn't make sense. But again, remember, probability alone, low probability alone, we talked about this last week. Low probability events happen all the time. Anyone go home and flip a coin 50 times? Anyone shuffle a deck of cards? Come on in, we got some. So, did anyone do that? Because we can have incredibly low probability events that do happen. Oh, come on, it's really not a big deal. You can.
I'm sorry, you're good.
Okay. Okay, well, we're glad you're here.
Thank you.
So we have low probability events. To see the universe being incredibly fine-tuned, very, very low probability that these properties, these features of the universe would align in just such a perfect way, it's actually not a great argument for God being here. But here's what I would say that is a good argument. When you combine low probability with something very purposeful. Okay, and I'll show you an example of this. So this is on a hike I did a few years ago, and I noticed these little things around on the trail. And I was like, that's a really low probability that those rocks would stand there. Now again, low probability events happen all the time. What is it about this that feels like, I think a person might have put it there?
Yeah.
What is it about this little strand? I mean, it's not like a huge thing. It's like a couple of rocks stacked on top of each other. What is it about these? I saw a couple more. I took some pictures. I'm like, I mean, it could have been by chance, but it felt really, really like somebody put them there.
Yeah.
And I got to the top of the mountain and I saw this. I was like, whoa, that's really, really low probability. Maybe have an idea. What is it that allows us to safely conclude that somebody put that there, that this wasn't an accident?
No. It's designed.
Right, how do you know that though?
It defies gravity, defies the natural law of
Yeah,
planet.
yeah. We don't see stuff like that.
And
That's
the rest of the rocks. Yeah.
Sure, we see this balancing act, but what we see is it seems to be there for a purpose.
Makes a statement.
Right. I saw these little ones, they're called cairns, and people put them on the side of trails to let you know, hey, you're still going the right way. Particularly once you get above the tree line and there's just rocks everywhere. How are you supposed to know where you're even going? And people put these up there. So they sort of defy what we would normally expect. They seem really finely balanced, and they also seem to be there for a purpose. All three of those things together, the low probability, the fact that these are sort of balanced in a very precarious way, and they seem to be designed for a purpose, we can safely conclude, and we do conclude, that someone put those there. See how that's different than purely low probability? Not just that it's very unlikely, but it also has a purpose, and it's been balanced together. And so, what we see is the universe essentially is the same thing. We have all these properties and all these attributes of the universe sort of balanced on top of each other. And not only do we see that being a low probability, we see it sort of going against what we would expect, and there's this strange feature about these properties lining up in such a way, it actually allows for life to exist. It seems that there's a purpose behind it. This is a very good analogy for what we see in the universe. The only difference is just imagine that stack of rocks goes to the moon. And again, that is not an exaggeration on just how finely balanced this stuff is. As we get in there today, I want to talk a little bit more about some math. I'm a math teacher, so I have to sneak it in somehow. But mostly I want you to understand how some of this stuff works. So we're going to be using something called scientific notation. I did mention it last week. I want to give you some examples and make sure that we talk about this. 10 to the n, that little variable n there, that means that I can put any number I want there. Anybody remember from last week what that little n, if I put a 6 there, for example, what that would mean? Anybody remember from last week? Yeah.
1,000,000.
It would be 1,000,000, that's right. It would be 6 0. So 10 to the 6th power, that's the same as 6 zeros, which is 1,000,000. All right, so that's what we're looking at here. We also talked about negative exponents, where if I made this a negative number, 10 to the negative 6th power, remember that's the exponents means something is multiplied by itself. So 10 multiplied by itself 6 times gives you 1,000,000. Negative exponent gives you a division problem, because it's the opposite of multiplication. So that is 10 divided by itself, you get 1 in 1,000,000 chance. So when we talk about probabilities or talk about very unlikely events, sometimes I use a negative exponent here to talk about, hey, this is a 1 in 1,000,000 event. That's what 10 to the negative 6 means. Or 10 to the positive means 1,000,000. Does that sort of make sense? Any questions on that? Give you a few examples here. We're going to check your intuition, all right, based on what I've told you here. And I don't answer this right away, because I don't want to spoil it for anyone if you do get it. But I'm going to give you 2 numbers here, 10 to the 40th and 10 to the 37th. We can definitely understand that 40 is bigger than 37. How much bigger? I want you to just sort of think in your head, how much bigger is it? 10 to the 40th and 10 to the 37. So come up with your answer in your head, what you think it might be. All right? Who's got a guess? How much bigger is 10 to the 40th and 10 to the 37?
1,000.
Yes, thank you. A lot of people think it's like a little bit bigger. Oh yeah, the number's a little bit bigger. 10 to the 40th is 1,000 times bigger than 10 to the 37th, because what I've done is I've multiplied by 10 3 more times here. That's 1,000. So you see a difference between 10 to the 6th and 10 to the 7th. That's a huge difference. You see a couple of bigger exponents there. That actually is a massive, massive difference. And again, in order to understand just how finely balanced the universe really is, we need to understand some of these big and small numbers. So, nice job. Peter, right? How many got that, by the way? Anybody guesses 1,000 times bigger? How many are like, oh, it's maybe 30 bigger? Right? It's easy to do that, right? to get these mixed up. Our intuition's really bad when it comes to big numbers. So here's some examples of big numbers. Okay, 10 to the 9th power is a billion. Again, it doesn't look that much bigger than this, but it's 1,000 times bigger. So when you hear governments talk about millions versus billions, they sound like the same number. They are not. Okay? And a trillion is 1,000 times bigger than a billion. So when you hear governments talk about a trillion, that is literally 1 million millions. My brain starts to hurt after I think about that. All right, so you can see again, there's a trillion again, 1,000 times larger than a billion. This is how we would express our current national debt, though I probably need to update that. So I have 10 to the 13th, that stands for 10 trillion, and then you have 2.8, so you're multiplying 10 trillion times 2.8, so 28 trillion, something like that. All right, what do we got here? Here's the number of seconds the universe has been in existence, approximately. So if we were to count up the 13.8 billion years the universe has been here and just add up the number of seconds, that's 10 to the 17th. We get some really big numbers here. Here's the number of atoms in Robert. I think I asked you that last year. How many atoms are in me? And the answer is more than last year. I thought that was a pretty good joke, so I wanted to tell it again just to completely ruin it, because that's what dads and teachers do. So if you were to count up all the atoms on the entire Earth, it would be something like 10 to the 50. And these are estimates, but when you're talking about numbers that large, I mean, maybe it's 10 to the 51, but that's so fantastically huge, you can actually be pretty confident you're somewhere in that range. How about this one? The number of atoms in the Milky Way galaxy. Milky Way galaxy is over 100,000 light years across, filled with untold numbers of stars and planets and asteroids and moons. And it's the number of atoms. And we're only at 66. Like, you look at this seems like sort of an unintimidating number. It's absolutely ridiculously huge. If you want to add up the whole universe, as far as what we can see of it anyway, it's called the Observable Universe. Pretty sure the universe goes farther than we can see. If you were to add up all the protons and neutrons, electrons, the whole universe, it's 10 to the 80th. Which again, doesn't look that big. It looks sort of unassuming number. It's an 80 next to a 10. And it's the number of all of the subatomic particles in the whole universe. So when I start talking about some big numbers, I want to give you some reference points. And we can refer back to this if you want to. So before we get even farther, I want to talk just a quick reminder about what we talked about last week, the Big Bang. Okay? So remember, the Big Bang, we have two possibilities for the beginning of the universe. One of them is that the universe is eternal. Right? The universe could be eternal. It doesn't need a beginning. Just like the number line goes on both directions forever, we don't actually need a beginning to something. We say God is eternal. We don't have to say who created God, because God has always been there. The same way the universe could be that. And if the universe happens to be eternal, then it doesn't need a creator, because it's always been there. Just like God doesn't need a creator. Okay, the other possibility is the universe did have a beginning, which means something had to put it here. Something needed to make the universe. All right, so that requires something had to create. Again, that doesn't necessarily imply the Christian God, but it does imply something put it here. Okay, and every scientific test we can do has confirmed that the Big Bang definitely happened. We are absolutely convinced that this happened. This isn't a question. We are far more certain that the Big Bang happened than something like evolution is true. Way more certain. It's not really a question. And we know that it happened, which implies, of course, that if it had a beginning, then something had to make it. All right, and I want to talk a little bit about how we know, because this is going to dive into what we talk about today a little bit, discussing our fine-tuning arguments. So, I want to talk about something about this CMB. Anybody know what the CMB is already?
No.
Okay, it stands for Cosmic Microwave Background Radiation. I promise I'll explain that in a second. Okay, but I'm going to give you a little history of what's going on first.
B.
There's a couple guys named Arno Penzias and Robert Wilson, and they were having trouble with some of their equipment. So imagine, it wasn't a TV, but they had some, imagine like an antenna. They were messing around with this antenna, and they kept trying to fix the picture of it. Again, it wasn't a TV, but it was similar kind of technology, measuring equipment using an antenna. Like before we had cable, like when we used to have little rabbit ears and stuff. This was in the 60s, and they were looking at this. And they had this static, and they're like, why can't I get rid of this static? This really sensitive antenna. And so they tried it at night, the static is there. Tried it at day, the static is there. Everywhere they point it at the ground, the static is there. What is this static? This is horrible. What the heck is going on? I can show you their antenna. It was pretty cool looking. And so they're measuring this thing in every direction. You can see that wheel that they can point it in any direction. The static doesn't seem to go away anywhere. You know when you fiddle with your antenna, you can kind of get the static to go away for anybody old enough to have that? So I'm poor enough to still have one of those. So we fiddle with it. Sometimes the channel doesn't come in right. And they were trying to do that essentially with this antenna. And this is a really big, sensitive antenna. They should have been able to get a good signal. And they could not get rid of this static. What the heck is this? So they did a lot of investigations. And they eventually figured out what they were seeing. What they were seeing, what their antenna was recording, is the heat left over from the Big Bang. 13 billion years ago, 14 billion years ago, almost. There's this giant explosion where everything sort of expands and is created. It was such a big explosion, you can still measure the heat of it today. Now, it probably wouldn't be described as heat, but we talked about this last week. You guys remember we talked about redshifted light? Remember about that when we talked about the race car comes towards you, and it compresses those waves and it makes it appear higher. When it goes, when the race car is coming towards you, it goes, it's really high, and when it passes you, you hear that, you hear those radio waves, or the sound waves extend. When they extend, we hear a lower pitch. They extend because the thing emitting them was going away from us. Right? Light waves do the same thing. When there's something emitting light coming toward you, it will appear more blue. When it's going away from you emitting light, it's going to appear red. Just like when the race car is coming toward you, it compresses those sound waves, it appears higher. When it's going away, the sound waves appear lower. Now, essentially what we saw is that light wave is the same as a sound wave, right? When you are using your cell phone, it's actually transmitting light waves. When you cook your food in a microwave, it's using light waves, different frequencies of light waves, different periods. So the frequency that we can see is actually a very short period. If it goes really, really short, it's called radiation, and we think that's really bad, but it's all basically light in one way or another. We can only see a part of it that's very small in the spectrum. If you stretch light out really, really far, it looks more and more like this, and you have these really stretched out waves. In fact, if you look at, have you ever seen an infrared camera? It's measuring the heat of different objects, where something's really colored red when it's hot and things like that. What that's measuring is the light waves being emitted from heat. They're lower wavelengths, so you can't see them with your eyes, but we can create detectors that can see that light wave. So what they saw, their giant antenna was picking up these really, really cold, but a little bit of heat left over from the Big Bang. And just, again, it's light waves essentially that are stretched out so much you couldn't see them. They're called microwaves. So when you cook stuff with your microwave, again, heats it up, same idea here. We can see microwaves throughout the entire universe. No matter where we point it, it's the same. It's really cool. And so they discovered this, won the Nobel Prize, was a big deal. And we started figuring out how the heck we were able to see that at all. Remember we rewound a little bit about the Big Bang. We saw that it was bigger in the past, or bigger in the future, so that means it must have been small in the past. everything is retreating away, so I brought my balloon this week. Okay, so I put some dots on here in Sharpie, and it totally doesn't even work. Needed a darker Sharpie, whatever. All right, so when you blow the balloon up, you see that everything's going away from each other. All the stars and galaxies are retreating away, which meant in the past it had to be smaller and more compact. There was a point where it was so compact, the whole universe itself was something like one giant star. It wasn't exactly a star, but you know how we can't see through the sun? It's so hot, like the sun is emitting light, but like you can't see to the inside of the sun. It's opaque. All of those boiling forces are together. At one point, the whole universe was so dense it was something like that. As it expanded, eventually it cooled down enough that you couldn't have nuclear fusion like we have in the star anymore, and suddenly all the light stops emitting, it stops becoming opaque, and you can suddenly see through the universe, and it emits all this light. Okay, all this heat and light, you can start seeing through it. Eventually it was like taking a picture of the early universe, and that's what they're seeing. So basically, we see this heat emitted from the universe about 400,000 years after it was born, which again is not very much compared to 14 billion. And then light was able to escape. That light that they were seeing in their antenna essentially was that. It's like a picture of the early universe. So we actually built a bunch of satellites to go and see this. We wanted to get a better picture of what the heck was going on in the CMB. The cosmic microwave background radiation, that was static throughout the whole universe. All of that heat left over from the Big Bang. So we built 3 satellites to check the CMB. First one was launched at the end of the 80s called COBE. So I think it's a pretty cool name, actually. Okay, Cosmic Background Explorer, and what it did was it got out of the Earth's atmosphere, so there wasn't all this other radiation, all this other signal getting in the way. It could get out and kind of get a really nice, perfect picture. Just like the Hubble Space Telescope is able to get better pictures of stars because the atmosphere and everything's out of the way. We put these things in space and we can get way better pictures. So this is the picture of the early universe that COBE took. Now those different colors actually represent different temperatures. Very, very subtle differences in temperature. Just as you would imagine, an explosion is going to have some hotter points than others, depending on what's going on, what's blowing up. We see that in the universe as well. Now, this bothered scientists when they saw this picture a little bit because they said, well, we see these hot points here, but galaxies aren't that big. Galaxies are much smaller on a cosmic scale than that. And so we need to build another satellite. We need to get better resolution. So they built another one. This one was called the WMAP, which stood for the Wilkinson Microwave Background Explorer, I think. Nope, Wilkinson Microwave Anisotropy Probe. I can't talk today. And it took a picture, and it was way better resolution, and this is what it saw. Again, all those different colors are different temperatures that it sees in the early universe.
What's the variance?
We're going to talk about that in a second. That's a great question. They were trying to figure that out. What is the difference between those temperatures? It's not very big. And again, you can see some places where there's more galaxies or less. And this is more along the lines of what they thought they would see. And they weren't done with that. And they're like, well, let's get an even better one. And so, anyway, here's a comparison chart. So you can see the different resolutions here. See the Penzias-Wilson antenna, and that's what they were able to detect. Just that line in the middle is the Milky Way galaxy, emitting lots of extra stuff, so that bar in the middle. But they were seeing this like faint buzz everywhere, that green color. The COBE was able to see, again, still the Milky Way, and because we're on the plane of the Milky Way, is very red, but then it saw the rest of that. And then you see the WMAP, just far, far better resolution. Able to see a much better picture of what the universe really looked like. And they said, no, we need to do one better. So they had one more. It was called the Planck telescope. And this is actually just launched about 10 years ago. And it took the best picture yet of the early universe. Cosmic microwave background radiation. And again, you can see kind of the difference between the 3 satellites they sent up. You can see how the resolution gets better and better. Now, you asked a really good question. So, the differences between the blue and the red pieces was only 1 part in 100,000. So, if you were measuring in degrees, the universe has the same temperature everywhere, it's just 1/100,000th of a degree less in some places, or 1/100,000th more. It's almost exactly the same temperature, and that's a problem for physicists to explain. We're going to talk about that in a little bit. But we're very certain the Big Bang happened. That's what I'm trying to point out here. We can actually see the explosion still. It's really, really amazing that we can still see this. And you'd think that it would cool down so much after 14 billion years you wouldn't see it anymore. We can still measure the heat that many years after. Okay? There are some counter-arguments. I told you I'm always going to give you the best counter-arguments for this, and I want you to decide what you think makes the most sense. Is God the best solution, or is there a physical, naturalistic explanation? So here's the kind of counter-arguments. The first one is called the steady-state theory. And the goal is, okay, how do we make an expanding universe eternal? This is what physicists were trying to come up with. And that's a problem, right? Because if you rewind, it gets smaller and smaller and smaller and smaller. So one of those guys came up with this idea called the steady-state theory. And it's a really bad theory, and nobody believes it anymore. But basically that the universe has to have a constant density. And so as it expands, it just magically appears, matter magically appears in the voids as it gets too big. This is really what people thought in the 70s. Not making this up. So they thought as the universe gets bigger, there's these big empty spaces, so matter has to spontaneously appear. Yeah, that's a bad theory. That doesn't make any sense. We see no evidence of that anywhere.
But the premise is that the universe has to be a certain density.
Correct.
Where does that come from?
Correct. The goal is we're trying to make the universe eternal so it doesn't need a beginning. And if it's always expanding, it can always be the same density. You can always rewind forever if it's infinite. And that was essentially the only way you could do it. And again, it was universally rejected because it violates pretty much everything that we see in the natural world and all of the physical laws of nature, and nothing about the universe gives us this idea this is true. Okay, there was a very popular theory in the 80s and 90s called the Oscillating Universe theory. Essentially, this idea is that the universe had a Big Bang, and expands. There's lots of stuff in the universe, right? Galaxies and galaxy clusters and black holes, and eventually all that gravity would have slowed the expansion down and then crunched it back together. All the gravity would have pulled it back together into one giant ball, super small, and then it would have blown up again. And then it would have contracted and blown up, and you see this eternal universe that inflates and contracts and blows up. And the problem is, that doesn't work either. We figured that out in the late 90s, that this is a bad argument because there's not nearly enough matter. There's not nearly enough gravity. We're short 95% of the gravity necessary to make this happen. It just isn't enough. Not going to happen. And so that has also kind of been universally rejected. The only naturalistic explanation that anybody believes anymore is called inflation. We're going to talk about that today in detail. Actually, might not have time today. We'll see. I did not plan a ton next week, so we can finish this if we don't finish. Okay?
Is the universe actually an ellipse, or is that just a schematic record?
That's a great question.
representation?
That's a great question. Yeah, it doesn't have to be this shape.
That's just the projection.
Yeah, it's just a projection. Kind of like when you look at the globe and you're trying to put a three-dimensional sphere onto a map. A lot of times it's in something like this shape, and that's the same idea. We have this sphere, and they're trying to put a sphere going all directions, and they're trying to map it on a two-dimensional space. So we put it in an oval, but it's not at all what we see. Great question. Fantastic. Thank you. All right, Big Bang creates problems. There's the horizon problem. This is a one that bothers physicists. And it actually relates to your question. What's the variance between the hot and cold temperatures in the universe? And we see that it's 1 part in 100,000. It's basically completely the same temperature, apart from some tiny little specks here and there. It shouldn't have had time to mix so smoothly. Who's got coffee this morning? A couple of you do. Anybody put milk in your coffee? All right. You ever seen somebody put milk in coffee? It sort of bubbles around and mixes. When you first put milk in coffee, right around the milk, it's really cold, even though the coffee itself was probably really hot. It takes a while for that milk to sort of mix in and all of the thermal energy to normalize so that it's all the same temperature. It takes a while. The universe is expanding so fast, it didn't have time to do that. It doesn't make sense that it would be so smooth, so consistent temperature. Okay? We see it as unreasonably consistent. Again, we saw that Planck satellite said that it was 1 part in 10 or 1 part in 100,000 in terms of temperature. What's on this issue of flatness? And this is a little bit harder to explain in a video that'll show it. But essentially the idea is this. If you have a triangle, this is another math question. How many degrees are in the interior of that triangle? Anybody know?
180.
180.
180, very good. Yep. If you add up any triangle, you add them all up, it equals 180. If you have a sphere and you draw a triangle, actually doesn't work that way. If you were to draw, and you ever see the paths of planes? If you ever see maps of planes flying, they always fly in these curved paths. The reason is, when you try to put a triangle on a sphere, it kind of looks like this. And you see these bigger angles. Actually, on a sphere, a triangle adds up to more than 180 degrees. There's another shape called a hyperbolic plane where they add up to less, depending on the shape that you're trying to draw this triangle on. And we don't understand, but it appears that the universe is totally flat. That's weird to picture flatness in three-dimensional space, which is sort of confusing, but it's perfectly flat, which is really, really weird. And the Big Bang, there's no reason either of these things should be true. The smoothness one particularly is important for life because if you have big clumps of heat here and there, you're going to get these giant, super dense galaxies spinning around each other, and you would never have like a planet left over that would be capable of life because you'd have asteroids and stars all smashing into each other constantly. It'd be way too dense. And then other parts would just be this cold void with nothing. So the fact that it's really, really smooth is actually necessary for life. The flatness problem is a little bit weirder, but I will tell you this, it relates to whether the universe would have contracted in on itself or not. And it also, life is dependent on it. It's also interesting, without it being flat, it would be really hard for us to learn about the universe, which is cool too. So I was going to have slide videos embedded in here, but I don't. It wasn't playing today, so I'm going to just a second backspace out and I'll show you the video. And I have captions on too, so you guys can read it. So,
Thank you.
yeah, you got it. So, here is video here. And I'll attach these later. You can watch them at your leisure if you want to.
Why essentially all cosmologists believe that it really happened.
Okay, so here we
The
go.
observable universe is impossibly huge. And I'm not exaggerating the situation here. It's so huge, 93 billion light years from one edge to the other, that those most distant points should never have had time to communicate with each other. And yet, at some point in the distant past, they must have been in contact. The cosmic microwave background tells us that they were once close enough together to become perfectly smoothly mixed. This smoothness of the CMB is called the horizon problem. And we talk about it in the last video. The horizon problem isn't the only troubling feature of the CMB. We can use the apparent size of the very subtle fluctuations in the CMB to measure the flatness of the fabric of the universe, of space-time. And the answer we get is very strange. Let me explain. A flat sheet of paper is flat, duh. Draw any triangle on one and add up the angles. It's always 180 degrees. Draw the same triangle on the surface of a sphere, which has what we call positive curvature, and the angles add up to more than 180. On a negative curvature, hyperbolic plane, a saddle-like structure, they add up to less. Triangles in 3D space obey exactly the same rules as on 2D surfaces. and their geometry measures the curvature of space. So now, think of those blobs in the CMB as the ends of very, very long triangles. We know the size of the brightness of those blobs. They're defined by how far sound waves could have travelled by the time the CMB was created. And we know how far away they are. They're really, really far. Using basic trigonometry, those distances tell us what the little angle at this end should be. It should be 1 degree, assuming the universe is flat. It should be larger if the universe is positively curved, smaller if negatively curved. And yes, it's pretty much exactly 1 degree. Based on the precision of our measurements so far, we know that the curvature is within 0.4 of 1% of perfect flatness. Okay, so what? The universe is flat. No, actually it's extremely weird. An expanding universe doesn't tend to stay flat, even if it starts that way. Analogy. One way to bowl a strike is to keep the ball near the centre of the alley all the way to the pins. If the ball isn't moving fast enough, then any initial deviation from dead centre will send it towards the gutter. Same with the universe. If the centre of the alley represents a flat universe, then the gutters represent extreme curvature in the positive or negative directions. If the universe starts out even a little bit not flat, then that not flatness will amplify quickly. So, if our universe is flat to within 0.4% now, then in the first instant, the universe had to be flat to 1 part in 10 to the power of 62. That's like rolling your ball really, really slowly and having it stay within 0.4% of the centre of the alley. And the alley is a light year long. Nice bowling, universe. This flatness problem is just as much of an issue as the horizon problem. Both seem strange if we assume.
So, anyway, I think it's kind of an interesting video, so you can see the picture of what we're looking at here. 1 part in 10 to the 62. All right, remember some of those big numbers. That's really, really, really accurate. All right, if you were to line up all the atoms on Earth in a line, you're still 1 trillion times smaller than what you would need for this. Essentially, you have, imagine that giant long line of atoms, and you've got to shoot one with a bow and arrow, just one atom. And if you miss, the universe is going to collapse or expand in such a way that we would never be able to see anything. All right? And that's actually 1 trillion times better odds than what is actually there. Again, the numbers are so big, it's baffling. When we look at this, we're like, why on earth could this possibly be the case? So, let's see here. You gonna give me? Okay, cool. So that's what we're talking about here. And it seems extremely unreasonable that that this would be the case. Do you still want to proceed? No. Okay, cool. Thanks. And I'm sitting here, and we've already gone way farther than I thought, and not as far as I thought at the same time. Let me give you the best counterpoint for inflation, or for this, because what we see again are those cairns perfectly stacked up. We see evidence for design. We see really low probability. We see the universe seems purposely designed for life. So that seems really like a very strong argument. A lot of physicists find this incredibly compelling, and they're like, man, this really feels like there's got to be a God here. So the best counterpoint that I can find is something called inflation, and this is basically the atheistic version of how the universe came to be. We don't have time to talk about this in great detail right now, but I do have a video that will introduce it to you. I think there's a lot of problems with this argument. The biggest being there's absolutely no evidence whatsoever to support that it ever happened. Though it does make some pretty math problems. So I want to show you that, and we're going to have to finish this next week. But I do want to get you started on, that's the wrong one. So, let's see here. So I want you to watch the same guy. This is a pretty good.
Have direct evidence from those very early stages.
Okay.
But there are some clues still visible at later times, and those clues tell us we've missed something huge. Let's undo our rewind a bit. Fast forward, again to 400,000 years after that crazy first fraction of a second. The universe is space-sized, but it's still 1,000 times smaller than the modern universe. It's full of this hot glowing hydrogen plasma, but at 400,000 years, it's cooled down just enough to form the very first atoms, and in the process, release the cosmic background radiation. We now see this light as an almost perfectly smooth microwave buzz across the entire sky. That smoothness tells us that all of the material in the universe, when the CMB was released, was almost exactly the same temperature, around 3000 Kelvin, varying from one patch to the next by at most 1 part in 100,000 across the entire observable universe. Why is this so weird? If you have a cup of coffee and drop in some cold milk, it'll all smooth out and become the same temperature after a bit of time. Well, the universe works in the same way. But, based on the simplistic expansion you predict from general relativity, when the CMB was released, there just hadn't been enough time for this mixing to have occurred. See, in order for the most distant patch of the universe we can see in that direction to have the same temperature and density as the most distant patch in that direction, there needs to have been enough time for something to travel between those points, to diffuse and even out that heat. And there just wasn't. Not even for light, the fastest thing that there is. Let's take this grain of sand-sized universe at 10 to the minus 32 seconds. A photon emitted on one side of that grain wouldn't have time to get to the other side, not even in 400,000 years. See, although light is fast, those opposite edges of the universe were travelling apart even faster. Another way to say this is that those edges of the universe have always been beyond each other's particle horizons. A quick refresher, here's a nice review episode on cosmic horizons. So, those edges shouldn't be in each other's observable universes. Not then, not now. This serious issue is called the horizon problem, and is a big deal that we need to sort out. The only way around this problem is to somehow have the universe, once upon a time, be small enough so it could easily get all nicely mixed together, and then, pow, blow it up in size, much faster than general relativity would normally allow. The theory that describes this pow is called inflation. The idea is the universe started subatomic, small enough that it was able to even out its temperature, and then entered a state of insane, exponentially accelerating expansion, in which it increased in size by a factor of at least 10 to the power of 26, so 100 trillion trillion, to something like our grain of sand size, at which point it slowed down to its regular expansion rate, but its edges are thrown way out of causal connection. Yet they look the same because they were once causally connected. This whole idea fixes our horizon problem. In fact, inflation solves a number of vexing problems with the Big Bang Theory. So well, in fact, that most cosmologists accept that something like this must have happened, even though we don't have any direct evidence for it. There are a number of explanations for how inflation might have happened, and some of them actually call into question our understanding of that very first instant of the Big Bang. In this sense, it may be more accurate to think of the Big Bang Theory not as a theory of the origin of the universe, but instead as a theory describing the period of expansion from a subatomic to a cosmic size. Aspects of this theory have such hard evidence that we know that the basic picture is right.
He's talking about the Big Bang right there, not inflation. He knows the Big Bang is right, inflation is purely speculative.
However, as with every really well-established theory, there are boundaries to what the Big Bang Theory currently explains. Those boundaries are being chipped away at all the time, perhaps the theory will eventually encompass a true origin for this universe. Or perhaps that question will take us far beyond the Big Bang. One thing I stand by. We can science anything, the origin of everything included. We'll get back to that on future episodes of Space Time.
So that is a good summary of what current cosmologists think of what actually happened after the Big Bang. Now keep in mind, there's absolutely no evidence to support this. None. Like we have no evidence whatsoever. It's a speculative theory produced by the same guys who came up with the steady state theory, actually. But it has a better mathematical underpinning and doesn't violate as many of the laws of physics. So what you're left with is kind of a difficult question for some people. So anyway, I think we talked about this. But basically the universe doubled 100 times in 10 to the minus 32 seconds. That's what they think happened. Like, that's fast. Imagine your house doubling 100 times in value in 10 to the 32 seconds. That's cool. It fixes the horizon problem, though, because it gives time for the universe to have mixed in temperature. And it fixes the flatness problem. Just imagine, like, instead of your bowling ball going super slow, if it's going super fast, you're a lot more likely to hit the middle of the pins, right? It doesn't have to be as perfect. Bowling ball really slow is much harder to get the pins than when you bowl it fast. And that's essentially the idea here, okay? But here's the question. What do you think? Which one do you think is a better explanation? One that is literally entirely made up. Has some cool math behind it. I can write lots of cool math problems though for you. They don't necessarily have to correlate with anything in reality. Or do you see the idea, okay, we have these really precise situations showing up. We're going to talk about more next week because we didn't get to as many as I thought, and that's fine. Or do we see maybe that there was some design here? Maybe all of these coincidences lining up, all of this really precise stuff, all this stuff pointing to there being a beginning, maybe there really was a beginning. And maybe that the person who put it here wanted us to be around. And so that's the question you have to answer for yourself, and I think you need to actually wrestle with it. Okay, but just remember that the inflation actually doesn't have any evidence for it at all. Okay, it fixes problems that are also fixed by an intelligence who wanted the universe to be here, and we actually understand how intelligence works. People putting things for a purpose, like those cairns stacked up on the side of the trail. We see that all the time. We understand how that works because we see it, what we build, for a purpose. Right? If you see a car going down the road, you don't assume that it was just accidentally thrown together because a tornado ran through a junkyard. You know somebody put it there on purpose and is running with a reason. Get your kids in soccer practice sometime. Okay. The other thing that's interesting is that inflation is continually modified. Every time they do studies and they find out, well, there's no evidence for it, they change it again and again and again. And it's not a good sign for a good theory if it has to be there. One thing we're going to talk about next week is that it's continually been modified. Now it includes a multiverse because they realize that there's even more fine-tuning in the universe than we talked about. In fact, the only way to get around the fact that this universe sounds designed is if there's already an infinite number of universes, and one of them would just happen to look like ours. Again, we have no evidence for that either. So, again, we don't have time to talk about current inflation theory. If you want to talk about it, we will mention it next week. But essentially, I'll just summarize it to say that if the universe was exponentially expanding at one point, maybe parts of it never stopped expanding exponentially. And so the idea is that there's some place, there's always exponentially expanding space that's creating universes all the time. And that's the idea that they try to present. And again, there's no evidence for it. It doesn't feel very scientific to me to just make something up that makes you feel good. Which is essentially what most materialists and atheists would accuse us of doing. in the first place, which I find very interesting, right? Like, oh, you just don't like the idea of there being nothing. It's like, well, actually I do. I just want the truth. Remember, Jesus, the way, the truth, and the life. I want the truth no matter what it is. And what I see is one theory that is kind of cobbled together, continually changed, and made up out of nothing. Another theory that explains stuff really, really well that we see examples of all the time. And for me, those two different options are incredibly compelling. We're going to talk next time, again, about the rest of inflation and what they think it's doing. But we're also going to talk about all these other coincidences, not just with the Big Bang, but stuff that we still see today that we can measure right now. Everything from the strength of the magnetic forces that hold atoms together. Well, atoms are held together with a strong nuclear force and balanced with magnetism, but that's another thing. Gravity and all these different properties of the universe. And we see them even more finely tuned than what we see already, where that bowling ball has to go right down the middle, 1 part in 10 to the 62. That's actually a pretty likely event compared to some of the ones that we're going to be looking at next time. We see this all over nature, super finely balanced. We see design everywhere. And you have to really, really stretch and make stuff up to get out of that. And so, to me, it's a very compelling set of arguments. In fact, many physicists have been convinced by this whole same idea. They're like, this doesn't make sense. I'm sorry, I can't go with the random chance thing anymore. So let's stop for today. I'm going to pray, and then again, we'll talk about more fine-tuning next time. We'll talk about cool stuff, like quantum fields and ripples in water and stuff. Lord, thank you for today. I hope that we learned some stuff, not just about the Bible, but also about nature, about how maybe, the metaphor of Genesis and the poetry of Genesis matches with what we see in science, and I feel like the combination of those is really beautiful, and I thank you for that. Please help us to discern truth, and not to be biased in what we want things to be, but rather that we can analyze with what things actually are. Teach us the truth, show us your way, help us to know you as a person, even as we look for your fingerprints in this world. We pray all these things in your Son's name. Amen.
Amen.
So, and if you want to stick around and chat with me about any of these things, you can. But it was a big lesson, and I didn't get through as much as I wanted to. But that's okay.